This is video 3 for the linear motion. In this one, we wanted to be able to describe motion. So for the Aristotle description of motion, the distance an object from its proper place was what was important. Galileo broke with this tradition by realizing that time is also an important ingredient. So Galileo described motion in terms of time rates of change. Now, a time rate of change of a quantity is divided by time. So if I have something that happens over a period of time, that would be a time rate of change. And usually we just shorten these things, we call them rates. A rate is anything over time. So the rates that describe motion are speed, velocity, and acceleration. To begin with, let's talk about speed. Things move, or things in motion travel certain distances over a given time. So an automobile, for example, will travel so many kilometers in an hour. Speed is a measurement of how fast something is moving. So speed will be a distance over time. Now for the units of speed, we can use any unit of distance over any unit of time. So miles per hour, kilometers per hour, inches per second, meters per second, meters per year. Any unit of distance over any unit of time is appropriate for speed. Now, if we take a look at the speed that something has in one instant, we call that instantaneous speed. That's what your speedometer does. It measures the instantaneous speed of your car at that instant in time. So when you glance down and look at it, that is your speed for that instant of time. Instantaneous speed. So a car does not always travel at the same speed. If you're on a trip, the speed usually varies. So imagine if you get stuck behind a slow driver, or if you're getting on an interstate ramp, or you drive through a town. Your speed's going to change for a larger trip. So that's why we need to distinguish between instantaneous speed and average speed. So for average speed, we take the total distance traveled and divide that for the time of the trip. This will give us the average speed. Now, since the average speed is the whole distance covered by the total time, it will not indicate the different speeds and variations that may have taken place during shorter time intervals. Now, in practice, we experience a variety of speeds on most trips, so the average speed is usually different from the speed at any instance. Now, if we know the average speed in time traveled, we can then calculate the distance. So, or we could use the total distance and the average speed and calculate time. And that's what GPS, like Garmin's and things like that, when they're estimating how much longer you have to travel, they take a look at your average speed and the total distance you have left to go, and then they can do very simple calculations. Okay, now we need to talk about velocity. Loosely speaking, speed and velocity are interchangeable. Strictly speaking, there's a difference between the two. So we can say that something travels at a rate of 60 kilometers per hour. That is speed. If we say something's traveling at 60 kilometers per hour to the north, now we are talking about velocity. So we can think of velocity as speed with direction. So, a race car driver. They're concerned with speed. How fast am I going? An airline pilot is very concerned with velocity. It's very important for an airline pilot to know where they are going. By custom, velocity alone is assumed to be the instantaneous velocity, and the same for speed. So if something moves at an unchanging or constant velocity, then the average and instantaneous velocities will be the same number. And the same is true for speed. Constant velocity and constant speed, however, can be very different. Constant velocity means constant speed with no change in direction. So for example, if I have something that has a speed of, let's say, 10 meters per second. After 0 seconds, it has traveled 0 meters. 1 second, it has traveled 10 meters. 2 seconds, 20 meters. 3 seconds, 30 meters. And we can keep going with that trend. So if something has a constant velocity, all of those numbers would be the same. If something has a constant speed, all those numbers would be the same. But there's also something else important. There's no change in direction for velocity. So if something is maintaining a constant speed, but traveling in a turn, it no longer has constant velocity. That's something we'll come to here in a minute. Okay, acceleration. This is how we change the velocity with respect to time. So we can change the velocity of something by changing its speed, by changing its direction, or by changing both its speed and direction. And that's what we call an acceleration. So, accelerations is equal to a change in velocity over time. So we're all familiar with acceleration in a car. So when we're driving, we experience acceleration. We tend to feel pulled back into our seat. If we hit the brakes, we feel pulled forward. Now keep in mind, that's just because of inertia. Remember, Galileo says that objects in motion stay in motion. Objects at rest wish to stay at rest. So when you're at rest, your body's at rest. When you hit the gas pedal, your body tries to stay at rest while the car moves underneath of you. And that gives you this feeling that you're being pulled back into your seat. When you're already moving, your body's moving at the same speed of the car. So when you hit the brake pedal, the car stops, but your body keeps moving. And that's why seatbelts are so important. So suppose we have a car that has an acceleration of 2 meters per second. And that's a unit for acceleration. Velocity over time. So if something has an acceleration of 2 meters per second, at 0 seconds, it has 0 meters per second of speed, or velocity. After 1 second, it has now increased its velocity by 2 meters per second. We can continue to follow that trend. So we see that acceleration is something that changes an object's velocity. Now notice that the unit for time enters twice, once for the unit of velocity and once for the unit of time. So we can use any unit of velocity. We can say miles per hour per second, kilometers per hour per hour. If the two units of time are the same, sometimes we write it as meters per second squared. And meters per second squared is the same thing as meters per second per second. So any of those units are acceptable. Now, acceleration applies to decreasing as well as increasing. When you apply the brakes, again, you feel pulled forward because of inertia. As the car's velocity decreases, sometimes we call that deceleration. And we also accelerate when we move in a curved path. So imagine that you're maintaining a constant velocity or a constant speed. So you're not getting any faster or slowing down. But you drive in a circle. Well, because you're driving in a circle, your direction is constantly changing. that leads to something called a radial acceleration. And the way we can calculate radial acceleration is taking the speed squared divided by the radius of the turn you're making. Now, in order for that to happen, there must be a force directed towards the center. If you're in a car, friction is providing that force, but that leads to a radial acceleration. Radial acceleration is very, very important when we talk about fighter pilots, because as they are going in a turn, they can have some incredible accelerations. So that one you don't have to worry about calculating, but it's still important. We need to address it, that there is that acceleration that does exist. Well, this will conclude video 3.